So we had some upset comments about the fact that these calculations have a heavy involvement with limits, but setting that aside, let's do a little bit more talk about the geometry here for source 1 and source 2. Pardon me? Yeah, sure, go to the office, pick something up. We got source 1 and source 2. And again, if I'm going to be using these two sources to project an interference pattern onto some distant wall, then I'm going to say that I'm going to actually call this wall a screen. I'm going to say it's a projection screen. And I'd like to say that this interference pattern is going to somehow create positive interference at some points and destructive interference at other points according to the rules that we've set out for constructive interference and destructive interference. And I'd like to say that, hey, look, here's my midpoint, here's my normal, here's a point, we'll call it point n, because we had theta n's and we had these integers we're dealing with. Let's call it point n, and point n is that distance L that we've already discussed away from the central point between source 1 and source 2, which, by the way, are a distance d apart. Then distance L, that is the distance between the midpoint between the two sources and some point on a projection screen. Because really we're talking about projecting not water waves, not even sound waves like when we talked about beats in the grade 11. We're talking about projecting light waves, and light waves actually interfering with one another to create destructive and constructive interference. So if you have light waves creating constructive and destructive interference, what would you expect to see on this screen? I mean, this is a thought experiment. What's that?
Band patterns.
Yeah, band patterns. Dark and light. Dark where there's destructive interference occurring at the point n on the screen, and bright where there's constructive interference occurring at point n on the screen. So we've got a theta value here. That's a theta relative to the normal that defines the angle between the L line and the normal. And we could say that sine of theta n could be equal to, and let's just use trigonometry. Let's call this guy delta x. And since it's for the nth point, let's call it delta x subscript n. We could say that delta xn over L, the opposite over to the hypotenuse, must be equal to theta n, the nth angle, for a given L value, for a given L line. Okay? I want you to remember that we've said once before, now this is just analyzing this picture and coming up with an equation that describes the picture. But we've said before that sine theta n is equal to the line AS1 over D, and that gave us this equation eventually. Sine theta n is equal to n minus a half lambda for destructive interference. And so I'd like to take this that we've come up with before and sub it into this value, setting the sine theta n's, or subbing in this value into the sine theta n spot, and you get n minus 1/2 lambda equals delta x n over L. So we actually have an equation that can describe how far away from the normal you'd find a destructive interference band, that is a dark band, as a function of the wavelength of the light that's being shone from these two sources and the distance the screen might be away from the sources. Now you're going to find multiple dark bands, but that's okay because you've got multiple integers that you could use for your n value. Yeah. Oh, I'm so sorry. You're right. I messed up and I didn't put my d value in there. Lambda over d, is that right?
Wouldn't it still be, yeah.
Yeah? Okay, I'm going to stop there for a minute.